Good evening, ladies and gentlemen. Welcome to the November Skep Talk presented by the Bay Area Skeptics. The Bay Area Skeptics is the oldest regional skeptical organization in North America. If you're new to the movement, we're skeptical, meaning that we believe in critical thinking, logic, and rational thought. What are we skeptical of? Well, it's a big umbrella that covers pseudoscience, claims of the paranormal, poorly tested medical practices, and many other assertions. And we embrace the scientific method as a useful tool to investigate such claims if possible. We work with many other local groups involving science and skepticism, including the Bay Area Science Festival, Wonderfest, the Center for Inquiry, North Bay and Silicon Valley Skeptics, and we partner closely with the Sacramento area skeptics every year to produce Skeptical, a one-day conference on science and skepticism. This year, we did not hold Skeptical because of COVID, but we're already planning it for 2021. Membership in the Bay Area Skeptics helps support monthly talks and our other activities, and we invite you to participate in making the world just a little more reasonable and spreading the word about what we do and why we do it. We're now on Patreon, which makes monthly donations very convenient. By the way, I'm Bill Patterson for the Bay Area Skeptics, and tonight I have the enviable pleasure to introduce tonight's guest speaker. When I was an undergraduate at a small engineering school in, of all places, Terre Haute, Indiana, I chanced upon a new student milling about in the computer lab. As I recall, we struck up a conversation and I found him to be a charming nerd who loved science and science fiction. As weeks went by, I would see him often on this tiny campus where nearly all of the 1,200 or so students, all male by the way, were at least acquainted with each other. At one point, I remember thinking to myself, man, this guy is really smart. Well, as it turns out, my instincts were dead on in this case. Don Lincoln finished his BS at Rose-Hulman Institute of Technology and went on to Rice University to eventually complete his PhD in experimental particle physics. He's the author of literally hundreds of papers which explore such areas as quantum chromodynamics, particle physics, and so on. And he was the co-discoverer of the top quark. This, of course, makes him the coolest person you'll ever know. To make matters worse for us underachievers, he was also on the team that discovered the Higgs boson in 2012. Don is research scientist at Fermilab National Accelerator Laboratory. Don has authored several books that are very good reads for scientists and laypersons alike. The Large Hadron Collider, The Quantum Frontier, and my personal favorite, Alien Universe, which is a great read for skeptics as well. Don is a fellow of the American Physical Society and the American Association for the Advancement of Science. And you may have stumbled across his YouTube channel where he has numerous informative and entertaining videos on all things physics. He even has lectures on the great courses. Some of them include The Theory of Everything, Understanding the Misconceptions of Science, and Inside Modern Physics, How We Know What We Know. Tonight, Don's talk is Dark Matter. Is the matter settled? He'll talk for about 45 minutes, and then we'll have about 15 minutes for questions. Ladies and gentlemen, please welcome Dr. Don Lincoln.
Well, hi there, guys. I'd like to thank Bill and the Bay Area Skeptics for inviting me. It'd be really nice if I could come there and visit you, but sadly I can't. But hopefully this will be a good a good substitute. So, without further ado, I'd like to start talking about dark matter. Now, I picked this topic because this is a skeptic society, and it would be reasonable for you to be skeptical about such claims that the dark matter exists. And so what I thought I'd do is I'd go through and I would tell you what we know, what we don't, and why. And at the end, you'll have, I hope anyways, a good understanding about what scientists think about this very big piece of the universe. And so I'd like to start that by pointing out that this is what I'm talking about. I'm talking about the entire universe. Now, if you asked most people who have some idea as to the stars and the galaxies of the universe, what is out there, you would come up with a pie chart of what the various amounts of matter and energy and what they are. And so if you look there, you would see that the stars and galaxies of the universe make up 10.3% of the familiar matter. But then there's more to just the stars and galaxies. There's also a subatomic particle called neutrinos, which are held over from the Big Bang, and they're almost as much contain almost as much mass as all of the stars and galaxies. In addition, there are gas clouds, and these are just clouds of hydrogen that you can't see with your eye, but can be seen with radio telescopes and things like that. So this is the pie chart of the matter of the universe, and we see, this is the familiar thing you see. Now I say that we're talking about the universe. I say this is everything, but the question is it truly everything? And that's where we launch into our story. So our story begins in the late 1920s, early 1930s, when a Dutch astronomer by the name of Jan Oort tried to measure how fast the Milky Way galaxy was rotating. Now, the Milky Way galaxy, the fact that there were even galaxies is relatively new. That was around 1929 when Hubble first found out that there were actual galaxies. Before that, that wasn't clear. And shortly thereafter, Jan Oort said, well, if it's a galaxy, it'll be rotating. And he took the known laws of physics and the amount of matter that he could see and tried to calculate the rotational motion. And what he found was that the Milky Way galaxy was rotating something like twice as fast as was predicted by the known laws of physics and what he could see. Now, this was, of course, in the 1930s, and astronomy was an imprecise science at the time. And it could very well have been that he had just made some sort of mistake. So nobody was super excited by it at the time, but this was the first hint that perhaps something was going on that we didn't understand. So as far as galaxies are concerned, I'd like to fast forward and introduce a woman by the name of Vera Rubin, who was a very influential astronomer. What she did is she took what Oort did and took it sort of to the next level. And so what she tried to do is she would try to calculate from very simple physics the orbital speed of stars inside galaxies. And so this is fairly straightforward. Stars orbit the galaxy in roughly circular orbits, and the force that makes the stars go in that circle is gravity. And so you can see here in the upper right-hand corner, I have the very simple equation that the orbital, the force that causes it to go into orbit is simply gravity. And from this, you can calculate the orbital speed of stars at all distances from the center of the galaxy. It's a little bit trickier than that because you don't have to use the mass of the entire galaxy. So for instance, if you are orbiting inside the galaxy, a certain amount of mass is attractive, and it's not the entire mass of the entire galaxy. However, as you go farther out, a star orbiting at the very outskirts of the galaxy, then the entire mass of the galaxy is relevant. Now, I thought about putting the math up, but that seemed like that might be too much for a Thursday evening. So, but you can take what we know about physics, and you can actually come up with a rotational curve. So right here, I drew just some axes. On the horizontal axis is the distance from the center of the galaxy, and on the vertical axis is the rotation speed. And what you calculate is this is what you should see. So near the center of the galaxy, stars should orbit slowly. As you go out to the periphery of the galaxy, stars should orbit faster and faster. And then when you get to the outside of the galaxy, where the stars trickle off and then there's just invisible gas clouds, you expect to see that matter would move more slowly. This is a very simple prediction. You can actually do a very, very good job of predicting this with simply your first year of introductory physics. But when the measurement was made, that's not what we saw. What we see, this is what's seen. So we see that towards the center of the galaxy, the stars move more or less as predicted. But in the outskirts of the galaxy, stars are moving much, much faster than can be expected. And this means there's something very, very wrong. What's wrong is unclear, and that's actually a large part of what I'm going to talk about tonight. Maybe we don't understand the mass of the galaxy. Maybe we don't understand the laws of physics. Something is very wrong. It is a mystery. And so when you unfold the mystery, just go back and think about it in the most basic sense. What we know, or what we think we know, is stars move in roughly circular orbits under the influence of gravity. So the orbital force equals gravity. And if you just unpack this in the very simplest of terms, it says, you have orbital on the left-hand side, gravity on the right-hand side, you have the equal. And the fact that they disagree either means you don't understand the orbital dynamics, you don't understand gravity somehow, or the equal sign is wrong. It really is that simple. That's the right way to think about this. So this is one mystery, but I want to tell you about a few other mysteries before I try and launch into how we hope to solve these things. So I talked to you about Jan Oort back in 1932 and Vera Rubin, who did her work in the 60s and 70s. But there's another chap by the name of Fritz Zwicky shortly after Jan Oort. He was doing a similar thing. But rather than looking at the rotations of galaxies, he was looking at clusters of galaxies. So a cluster of galaxies is many galaxies. It can be tens, it can be hundreds or thousands of galaxies held together by gravity. And he was looking specifically at a cluster of galaxies called the Coma cluster. And what he found was that if you looked at the speed of the galaxies and you tried to compare their speed to the amount of matter that you saw, the amount of matter should hold them in, but they were moving too fast. Bell writes, this cluster of galaxies should not exist. They should have blown apart. And in fact, Fritz Zwicky didn't know exactly what it was, but he came up with a term explaining what might be, and he called it dark matter. And dark matter wasn't proven, and it wasn't proven for a long time, but he was the one that came up with the term. So this is actually three mysteries: the rotation mystery, Vera Rubin's mystery of the rotating galaxies, and this mystery of clusters of galaxies that just didn't seem like they should even exist. And so let's be scientific about this. What do we really know? Well, what we know is we have mysteries. We have the Oort discrepancy, the spiral galaxy flat rotation curves, the cluster velocity dispersion, and large-scale structures of the universe, which I didn't talk about in the interests of brevity. So the way to think about this is to say these are the roots of the mystery. And we can then make this picture, this tree, rooted in these mysteries. Now, I can't take credit for this. A physicist by the name of Stacy McGaugh came up with it, and I stole it from him. But I like it very much, and I've used it many times. So what are the explanations of these mysteries? Well, remember I said that orbital force equals gravity. Well, this is just saying the very same thing. So if we look at this tree, we can go up the trunk, and it's just a decision tree. Do we understand the laws of physics? If we don't, if you look up the laws of physics, you have the laws of inertia and orbital motion, or you have the laws of gravity. And on the other side, you have the potential of missing mass. And then what kind of mass is it? Is it ordinary mass, or is it something exotic? And so if you're going to be a scientist, you have a hypothesis, and what you want to do is you want to cut off the branches of this tree. Now, there are various possibilities. If there is matter that is unseen and normal, they have names like machos. I'll tell you what those are in a minute. But basically, this is things like stars, planets, dark stars, black holes, things that you can't see, but have mass and cause gravity. Then there is another possibility that you have unseen and unobserved exotic matter. Exotic matter, by that I mean matter of the form not made up of the atoms that makes up everything that we're aware of. There's two different kinds. There's fast moving matter and slow moving matter. And then another possibility is that the physics is just simply wrong. So let's talk about two of these. And we will start by talking about this unknown matter called machos. And then I'll go and I'll talk about another possibility, this unobserved matter, this exotic matter. So the original, and this is absolutely the most obvious answer for this whole thing, is if galaxies are rotating too quickly, then maybe there's just matter that we can't see. There's nothing really all that fascinating about it. I mean, or it's at least interesting, but it's not shocking. It could be just black holes or planets that have been released from their suns and just moving through the cosmos, not attached to any stars. And before we were able to see things like the well, those are those things. And so, how would we study those? So, there was in the 1980s and 1990s, people looked basically for things like black holes that were out there, and we just couldn't see. Now, the way we did this is really absolutely most clever. We call these things massive compact halo objects. So they're massive. That makes sense. They're compact. They're the size of a star, say. They are halo, which means they are in the outskirts of the galaxy, and objects, well, they're objects. And the way we would see these is really very neat. We would look at distant stars. So we would look, say, in the Milky Way, we would look at either, say, the center of the Milky Way, or we'd look out to stars in like the Magellanic Clouds, which are small galaxies orbiting the Milky Way. And if this macho idea existed, this graphic here shows you roughly what it would look like. You would have this macho, this black hole would move in front of a star. Now, before the black hole moved in front of the star would have a certain brightness. As the black hole moved in front of the star, the gravity of that black hole would bend the light from the star, and briefly it would be bright. And then the black hole would move out from in front of the star, and the star would return to its original brightness. So this is the signature that you would expect to see if there are these machos in the Milky Way. And so this experiment, or actually many versions of this experiment, was done in the 1980s and 1990s. And so here's sort of a representative bit of data. So there you see a star field, and if you look really close, you can see a little cross there. There was one of these stars that became brighter, and for a reason that we couldn't see. So these experiments, they had really, one name was Macho, another was Ogle. They always have clever names. And so here on the right-hand side, you see an instance where a star had a certain brightness, and then it became much brighter, and then it returned to its original brightness. And very importantly, when we looked at the star, the color of the star changed the same in both the red light and the blue light. And that's very important because, after all, stars are variable potentially. Some will get brighter, some will get dimmer. But if they are the same, it gets brighter and dimmer exactly in all colors, then it's evidence for what they call this lensing event. And so this is an example. Now, what happened when this was all done is we looked and we saw some of these things. We actually saw these machos passing in front of distant stars. And so that was great. That meant that we could see them, but we also saw enough of them, and we were able to calculate what mass could be accounted for by black holes floating around in the periphery of the Milky Way, and there just wasn't enough. That is not the reason that the Milky Way rotates too fast. So that is one thing that we can rule out now, saying that dark matter, whatever it is not caused by black holes. So then there was another idea. Suppose there was some sort of unknown dark matter. We don't know what it is, but what do we know about its characteristics? Is it, if you think of it as sort of a gas, are these dark matter, is it moving quickly or is it moving slowly? And so there's another way to test this. So one question is, how does the dark matter affect galaxy and cosmic structure formation? So if the dark matter is what we call hot dark matter just means that it's moving very quickly, then it has what it would do is we would take when the Big Bang occurred, you had the gas of hydrogen relatively smoothly across the universe. And what would happen is it would clump together in big structures, and then those structures would break up into smaller structures, and eventually we'd see the galaxies we do now. If instead the amount or the type of dark matter that was out there was moving slowly, it would do something differently. What would happen is it would first clump into small structures, and those structures would combine together to make bigger and bigger structures. And then we get to the galaxies that we have now. So we have two very different signatures as to what the universe would look like if we had fast-moving dark matter or slow-moving dark matter. And so this is just like a little cartoon, but here is a more interesting simulation. And so on the left-hand side, we see this is what the universe, early universe would look like. So what you're seeing here is all of these little dots here are individual galaxies, and what the dark matter would be, that's on the top. And so you see sort of on the left-hand side this diffuse thing with some very small strands through it. And on the bottom, this is what would look like in the proximity of a galaxy. So you have sort of a diffuse looking thing with a couple of hot spots around here and there. On the right-hand side, we have what you would see if the dark matter was moving slowly. And you see it is a much more filamentary structure. You have sort of ribbons and voids, whereas on the left-hand side, it's more like a cloud. And then if you look down in the bottom right-hand side, you can see close to a galaxy, you see that there are these little dots. These are clumps of gas. These are small satellite galaxies of big galaxies. So this is great because that means that we can use these predictions and then look at this universe and have it tell us whether or not dark matter is fast moving or slow moving. And so here is some real data. So on the left-hand side, we have a picture, a survey of the universe to 2 billion light years away. And what you can see is there is this filamentary structure. There are ribbons and voids, and each dot here is an individual galaxy. And then you can zoom in and just look at, these are individual galaxies, but the on the left-hand side, this is just what we saw, we meaning astronomers, when they looked very, very deep into space. And the data very, very clearly favors cold dark matter. We now can say with some confidence that dark matter, whatever it is not moving very quickly. And so we can go back to our tree and say, we're going to start doing what we wanted to do. We're going to rule out some of these things. So we were able to rule out machos because there just simply weren't enough of them, and that just lops off that branch of the tree. And we were able to rule out the hot dark matter. So we see over here on the left-hand side, what's left is some kind of dark matter that's exotic and slowly moving, and we'll get back to that. But we have this huge bow on the right-hand side where we don't understand physics. And so let's take a look at that. So there is an idea that says, okay, maybe this dark matter thing is completely nonsense. What's really happening is we just don't understand the laws of physics properly. And so how can we determine whether or not which one of these is true? So there's a sort of the perennial question, modified physics versus dark matter. Well, if it's modified physics, then what does that mean? That means that there are two components in a galaxy. There is the stars that we can see, and then the gas that surrounds it. So there are two components, and they come together. If dark matter is right, then there are three, and I put question mark because there, in principle, of course, could be multiple types of dark matter. But if there's dark matter, there's ordinary matter, the stars and gas, but then there's also this dark matter. Now, we don't know what dark matter is, but you can think of it as sort of a gas of some different kind, something that doesn't interact and doesn't emit light. And so the fact that there are these two different things gives us a handle on maybe we can actually use the two of them to separate which is which. So there's some questions we could ask. One of the questions we could ask is, well, what if general relativity is wrong? General relativity, of course, is Einstein's theory of gravity, and it's a fantastic theory. I mean, I could spend an entire talk talking about exactly how right it is, but maybe it's not complete. Maybe there's something about it that isn't quite right. So people actually think about different ways, possibilities of coming up with alternatives for general relativity. Now, I don't want to go through all of these things, but this kind of gives you an idea of the sorts of ideas that people are thinking about when they talk about variations of general relativity. So general relativity is the big brownish blob, but then you have things like massive gravity. Maybe there are different kinds of fields, and then there's all these ideas that people have thought out, predicted. Say, well, maybe there's something just wrong with general relativity, and many of these can be tested. This thing over here on the right-hand side says that these are gives you a color coding for whether or not things can be tested by looking at various gravitational waves. And the only really takeaway message for that is a lot of ideas have been proposed, and because of the different color codes, some of them can be tested using the gravitational properties of gravitational waves. And so I just want to talk about, because there's only limited time, to show you an idea of why general relativity is well regarded, because there's a lot of reasons why it's well regarded. But one is very, very impressive, and one is to study two what they call pulsars. So pulsars are neutron stars. They're stars that were once heavy. They used up all of their fuel. They have collapsed down to the size of a city. Two of them are orbiting one another. It was discovered in 1974. There is a pulsar which has a period. It gives a radio pulse towards the Earth with a 59 millisecond frequency. It's orbiting a invisible companion with an orbit of about 8 hours. And the 1.2 million mile orbit between these two shrinks by about half per day. And it shrinks due to the emission of gravitational waves, which are one of the predictions of general relativity. And this is an absolutely fantastic plot. I absolutely love this plot. So the data shows how much the orbital period changes over time. And you can see we're talking over a considerable amount of time. From the 1974 through about 2000, it changed by the 7.8 hour orbit changed by a few tens of seconds. And the line that we see here is the prediction from general relativity. Now, this is not a lock that general relativity has been tested in every possible way, but it gives you a sense of just how precisely general relativity has been tested. So we know general relativity is largely right. It doesn't mean it's completely right, but hopefully, and there have been many more tests of this, but people think general relativity is a very, very strong theory. So there is another option. I'm talking about how gravity could be different. There's the possibility that maybe, just maybe, we don't understand the laws of motion. If you took physics, F equals ma, so Newton's law of motion. So there was a chap by the name of Mordechai Milgram back in 1983, and he said, well, maybe Newton's law of motion is incomplete. Maybe F doesn't equal ma for all accelerations. He said, well, perhaps at very, very low forces, F is lower than mass times acceleration. So this is true for large distance from the galaxy center, and that would mean, by constructionist theory, would keep the velocity of stars from changing. So if you take his idea that basically says that Newton, while correct at very, very small accelerations, wasn't quite correct, and you modify Newton's law of gravity, you can get rotation curves like this. Now, I showed you one with a galaxy on it. The green curve is what, for a specific galaxy, happens to be NGC 1560, that the green curve shows you what you would get from Newtonian physics, from Newton's law of gravity and Newton's law of motion. But if you take Milgram's modifications, then you get the red curve, and you see the red curve agrees very well with the data. And so this actually, for a long time, was very attractive to me. I thought, well, maybe this guy was really onto something, and I like that very, very much. It's this theory, or this idea of his, works very, very well for individual galaxies, but it works less well for other mysteries. So the mysteries of the clusters of galaxies, and other things that I didn't have time to talk about. But there's something to this. I mean, it agrees so beautifully that there's, at least something to the equations, if not to the underlying physics. So the question is, can we distinguish between can we distinguish between uh, uh, modified dynamics or dark matter? So there are a couple of really strong ideas that I really like. And so one of these was astronomers looked at galaxy clusters. So these are clusters of galaxies. They could be, a cluster of 100 galaxies and a cluster of 1,000 galaxies or something like that. So galaxies consist of the literal stars of them. That's a small amount of the matter in a galaxy cluster. There's the hydrogen gas that surrounds them, that's medium. And if dark matter is real, then that's a large component of the amount of matter in clusters of galaxies. So the question is, what happens if two galaxy clusters combine? Do they have different outcomes for dark matter and modified Newtonian dynamics? Well, here I have just a little kind of cutesy picture. So let's ask, what happens if you have two clusters of galaxies pass through one another and you don't think about anything other than the galaxies themselves? What happens is those pass right through one another. They jiggle around a little bit, but they basically just go through. Well, now let's add gas to the galaxies. So in that case, what happens is as they pass through one another, the galaxies continue, but the clouds of hydrogen gas bump into one another, and you end up with the galaxies separated from the hydrogen gas. So, is such a thing seen in nature? And the answer is yes. Not very often, but there are a few. So there is a thing called the bullet cluster, where two clusters of galaxies pass through one another. And here's the name of it if you ever want to look it up. So let me, that just looks like a bunch of stars to you. You don't really know what it is. In fact, most of those are galaxies, not stars. That little blue thing in the sort of middle center, that's a star, but most of what you're seeing here are actual galaxies. And so here I'm drawing circles around these. These are this is the locations of the galaxies after they've passed through one another. Now, we can use a different type of astronomy, not visible light astronomy, but using an X-ray telescope that will look for hot gas. And so if we ask, where is the hot gas after this collision of the galaxies, what we see here, this red stuff, that's the hot gas. And so remember where those circles were. Those circles were a little bit farther away from those things. And so we see where the galaxies are, and now we're seeing that the hot gas is between the two galaxies, which is what you'd expect when clusters of galaxies pass through one another. The gas clouds collide and they stop in between them. And now the question you have to ask yourself is, where is the total mass of the universe? Where can you see that? And this is where you see it. This is the matter profile from a thing called gravitational lensing. So what you can do is you look at more distant galaxies and you see how their light was distorted from the passage through the cluster, and you see that there is more mass where the galaxies are, and there is the mass is near the galaxies, but not where the hydrogen gas is. Remember, the hydrogen gas is more than the mass of the galaxies. And so this is sort of pretty important, that the dark matter and the extended gas clouds are separated. Remember that if you say that this is just as a ratio, if you call the amount of stars equal to 1, the amount of gas is about 10 times that, the amount of dark matter is, I don't know, maybe 50 times that. And so since the mass stays with the stars, which have a small amount of mass, then that means that this dark matter was able to pass through, unlike the hydrogen gas. And so this thing, the bullet cluster, favors the dark matter hypothesis, not the modified physics hypothesis. It's not a lock, and there are some criticisms which people might raise about this, but I think it is more persuasive than than not. And this was probably the first thing that made me go from thinking, well, modified dynamics might be right to, well, maybe that's maybe not the right thing. In addition, there is another, and this is a really, really nifty thing. So there are, every galaxy has a certain amount of matter and a certain amount of dark matter, according to the dark matter hypothesis. But there are a subset, a very small subset of galaxies. This one here, particular one, NGC 1052 DF4, it seems to rotate exactly according to the laws of Newtonian physics and the amount of matter we see. It seems to have no dark matter at all. Now, when you think about this, that's really weird. I'm telling you that this particular galaxy, it's a very small galaxy. It's relatively close to ours. It's only 62 million light years away. It rotates as if there is no dark matter. Well, if there's no dark matter, then what I'm telling you is that this is incredibly good evidence for the existence of dark matter, which is very hard to believe. Now, why is that? Well, if a galaxy has no dark matter, then dark matter can be taken away. Whereas if it had the explanation for the quickly rotating galaxies was modified physics, then it's hard to imagine how you could take it away. So this is an incredible irony. If you could find galaxies without dark matter, then it's very strong evidence that dark matter is real. And so we get back to our little graph here. We've ruled out machos, we've ruled out fast-moving exotic matter, and now from the fact that general relativity works very well, and both the bullet cluster and these galaxies without any dark matter, we're able to rule out, and I don't, maybe not perfectly, but we can certainly disfavor these branches of this tree. And that leaves us with this yellow circle up here. Maybe this is the place to look. And this is the idea of dark matter. This is the hypothesis of dark matter. So let me give you the dark matter thinking of, say, from, about 1990 to 2015. And why do I say over that range? Well, in about 1990 is when we pretty much ruled out machos and we ruled out the hot dark matter. So in this time period, this 25-year time period, dark matter is thought to be a massive particle with a mass in the range of, say, 20 times the mass of a proton to maybe 1,000 times the mass of a proton. This dark matter, whatever it is, it's not a proton, it's not a neutron. We don't know what it is, but it doesn't have any of the structure of protons and neutrons inside it. It has no electrical charge, because if it had electrical charge, we'd see it. And so the name we have for this, if we had machos, we now have WIMPs, for weakly interacting massive particles. And the idea is that there's just some new kind of matter that nobody's ever seen before, but it has the property that it has mass, doesn't emit light, and that's what dark matter was thought. Now, if dark matter exists, I showed you a pie chart of the matter of the universe, of the regular matter. But now when you include dark matter, what we think is something that's really quite staggering. All of the stars and all of the galaxies that we see and all of the beautiful Hubble telescope pictures is about 0.5% of the matter and energy of the universe. If we include the hydrogen gas that we can't see with our eyes, but we can see with radio telescopes, and neutrinos, which are a subatomic particle that people like me study, we find that this is all of the matter of the type that we're made of. This is the matter of atoms. It's about 5% of the matter and energy in the universe. Dark matter, from our surveys of seeing how fast galaxies rotate and the galaxy cluster motion and things like that, seems to be about 5 times as much as the ordinary matter that we see. And then there is yet another thing, not part that we don't have time to talk about, but a thing called dark energy. Dark energy is an energy field that permeates the universe. It's the biggest thing in the universe in terms of energy content. It's making the universe expand faster and faster. But dark matter is what we're talking about here. So this is really kind of staggering, especially for young people listening to this. The matter and energy of the kind that makes up us, all of chemistry, all of known physics, is 5% of the universe, which means we don't know 95% the energy matter in the universe. There is a discovery there for some very bright young person to figure out, and someone's going to get a Nobel Prize over this. All right, but let's talk about dark matter. If dark matter is real, and if it is this WIMP, the weakly interacting massive particle, how would we go about finding it? Well, there are several different strategies that we can do this. We have the direct method. The direct method is maybe dark matter is actually passing through the Earth right now. Maybe dark matter will smash into the nucleus of an atom or something, and we will see the interaction of dark matter in detectors here on Earth. There is the indirect method, which is really kind of nice. In indirect method, maybe there is dark matter, and the dark matter can interact in unique ways out into space, and maybe we will see dark matter interacting. And there's several ways we can see it. We could see maybe dark matter interacting in the sun and giving off particles called neutrinos, or maybe dark matter interacts out in galaxies, and when it annihilates, it gives off gamma rays. And we'll just look out into space and see the signature of things out there that we can't explain with our known physics. And then finally, there's the possibility of producing dark matter at large particle accelerators. So that's what I do. And, Bill talked about many of the papers that my colleagues and I have published, but some of them have been looking for dark matter. And sadly, I can tell you we haven't found any yet. And I'll talk very briefly about that. So indirect searches for dark matter. So this is a picture of the Milky Way from the edge on, and above above and below the Milky Way, there is a glowing cloud of gamma rays. And for a long time, people thought that this gamma rays came from dark matter, and that's still a somewhat viable hypothesis. But the problem is that these gamma rays and X-rays that are coming towards us, there's lots of ways they could come, and these gamma rays could come from astronomical sources, things that we know. So pulsars are one thing. They're just quickly rotating neutron stars, and they can cause these X-rays and gamma rays. And the problem is unless you know your astronomy incredibly, incredibly well, it's hard to imagine how you will able to find dark matter unambiguously in space. So people look for that, but it's going to need backup. So you can also make dark matter in particle accelerators, and one way we do this is the Large Hadron Collider, where I do my research, where you smash protons together. The protons use Einstein's equation E equals mc squared. It converts the energy of these collisions into matter and dark matter. And since matter and dark matter don't interact rather, in the collisions, what will happen is you will see collisions where energy disappears because it escapes our detector. And we have looked for this very hard, and we see no evidence for that. And so that leaves dark matter that sort of exists in the wild. How would dark matter particles interact with ordinary matter? Well, they might pass through a detector and bounce into the detector and shake the atom. And so this is the direct detection, and we look for this in deep underground mines, say a mile underground in various places. So we've looked for this. Basically, what we're looking for is dark matter in the solar system passing through the Earth, occasionally hitting our detector and seeing it. So what sort of luck have we had that? Well, these cold dark matter searches, these direct searches, there is one experiment that has reported a signal that varies. So you see this picture here. This is the Earth going around the sun. The sun goes through the Milky Way. And the idea is that there is basically a wind of dark matter that passes through the Earth. And because the Earth orbits the sun, half of the year it's moving into the wind, and half of the year it's moving out of the wind. And so if that's the case, when you're moving into the wind, you would expect more collisions. When you're moving out of the wind, you expect fewer collisions. And this is what the data looks like. And this is from the DAMA experiment. You see on the left-hand side, the red data, where you see the years. And so every year it goes up and down. It gets more and less. But the data there is hard to see. But then the experiment got upgraded with a different technology, and they now call this Dama Libra. And so on the right-hand side, you see the data with a superior and improved detector, and you see the data points that very clearly follow that wiggling pattern. So that is, you might think, well, that's it. There's the clincher. Everybody sees it. Dark matter is there. Send them to Stockholm, give them their Nobel. But the problem is that other experiments with supposedly better resolution don't see what they see. So there's a lot of dark matter experiments. They're all over the world. You have them in Canada, the US, see them in Europe, and then in Asia, where China, Korea, and Japan. And they're all looking. And the Dama experiment claims to see something, but none of the other guys do. So let me just give you a quick summary of the dark matter searches, the direct one. You have the Dama experiment, and this one reports seeing a signal, and so that's really very promising. However, far more sensitive experiments, and I mean like 100,000 times more sensitive, they don't see it. They don't see nothing, absolutely nothing. And so that really is kind of weird that one experiment sees it, but much better experiments don't see this. And then, of course, where does that leave us? Well, that tells you that except for the Dama experiment, none of the dark matter experiments have seen anything. And so now what we've done is we have ruled out all of the branches on our tree, which is very embarrassing because the roots are still there. The mysteries are still there. An explanation has to be found. We don't know what it is. So now what? Well, dark matter is still favored, but the standard WIMP idea seems to be ruled out. There is other possible solutions, things called complex dark matter, which says that maybe dark matter is just more complicated than we think it is. There is a really neat idea that maybe dark matter is what we call a superfluid, which means that it moves without interacting with each other, and that's pretty cool. Could be something else. So, or maybe we just need to rethink our ideas about gravity. So while I told you we ruled out everything, now we're getting to the point where we have to be more creative. So we have to rethink cold dark matter. Maybe there's something about it that we haven't understood. Where those red circles are, those are pretty much still ruled out. The machos can't be dark matter. Dark matter can't be hot. It has to be cold. But now maybe modified gravity is real. Maybe dark matter, cold dark matter is there, but it's something that we haven't figured out. There are a lot of creative ideas, and we can discuss some of those in the Q&A. But when you get right down to it, when you talk about dark matter, we don't know. We know many of things of what it isn't, but we don't know what it is. But we know that there are mysteries. There are mysteries to be solved. There's a solution there, but we need to use our scientific method to figure out what the heck it is, and we just don't know. And so as we close, I think the right way to think about this is to take Sherlock Holmes' idea, is you have to first eliminate the impossible, and whatever left, however improbable, must be the truth. And this is something that we are studying. I hope that in maybe the next 10 or 20 years, we will get a handle on this. But the reality is we don't know what dark matter is. We just know that there are mysteries to be solved. And so it's a wonderful journey. It's a fascinating journey. If young people are listening to this, it is something to get into and study because there's a lot of experiments and we don't know the answer. And with that, that's all, folks.
All right, thank you, John. That was terrific. It makes me think I should have paid a little bit more attention in Dr. Kiker's class, but
absolutely, he was great.
That was really, really cool. I wanted to start with my own question, if I could.
Sure.
What, if any, effect does dark matter have with respect to the so-called heat death of the universe? Does it have something to do with that?
No, the heat death of the universe is just the universe will expand forever. And as recently as 1998, we realized that there is an energy field called dark energy, which is causing the universe to expand faster and faster. So what that means is the galaxies are moving away from one another. And in the very distant future, we won't see distant galaxies. We'll just see a couple of galaxies near us. The stars will burn out. Eventually, they will die. They'll collapse into black holes or white dwarfs, and their heat will dissipate away. And so when they ask, will the universe die with a bang or a whimper? The answer is most certainly a whimper. And dark matter is just one of the forms of matter that is there that will lose energy and cool off, and eventually the universe will go dark.
And what are we talking, like 10 or 15 years from now?
Yes, definitely 10 or 15 years. No, I mean, we're talking much, much longer than that. I mean, it will be hundreds of billions of years before everything is gone. Um, Matter will fall into black holes. The black holes will eventually evaporate. We are talking the very, very distant future. So I'm sorry, you still got to pay your taxes.
Darn. All right. There's a really good question here from, I'm not going to get the name right, but it's Jim. Looks like Lilienthal. I'm reading, have multiple galaxies without dark matter, standard Newtonian rotation been found?
A few, not very many of them. It's actually relatively new. I know of two. There's one DF4 and another one called DF2. There was some conversation about whether or not we should even believe the claim that these galaxies are rotating at the right amount, because there was some question about whether we knew their distance. And if you don't know their distance, well, back up. How do you know how much mass they have? You can't get out there and measure it. So the way you do that is you know something about the stars, and then you see how bright they appear in in our telescopes. And by using just simple physics, you see how bright they appear to be, and you know something about the stars, then you know how far away they are. And there was some question about whether or not we understood the right distance, because if you thought they were the wrong distance, then you would think they have the wrong mass. But that seems to be resolved, although there's definitely an ongoing conversation. So I know of a couple of these very diffuse galaxies, but people are looking at them, and I expect more to be found, or not. I mean, it's science. I mean, it's the sad thing about science, or the exciting thing about science, is you don't know what you're going to find, and but they seem to have done it right, and we'll just have to wait and see if we see more of them.
Okay, there's another question here from the Bay Area skeptics. We've ruled out most branches of the tree with experimental evidence, leaving only one or more. What kind of experiment could falsify or verify the last branch? And what happens if that experiment rules out the last branch? Where do we go from there?
Well, then you got to be smart. You got to be creative. So until recently, I mean, I said, what was it, from 1990 to 2015? If you asked most physicists or most astronomers, they would say, yeah, we kind of know what dark matter is. It's basically like a heavy neutron, a heavy stable neutron. There's a gas of it floating in space. There, if you do the, what we thought there was, if in any one fist-shaped volume anywhere here on Earth, there's one dark matter particle in it. So that's what we thought. But that didn't work, or it doesn't seem to work. So now there are some new ideas. People have thought about, well, maybe dark matter is more complicated than we think it is. Maybe in the same way that ordinary matter can make atoms, maybe dark matter has forces that ordinary matter doesn't see that makes dark atoms, and could make even dark, somewhat clumpy bits of matter. So we're looking at something like that. There's a recent idea called superfluid dark matter, which says that there's two forms of dark matter, like two phases. And you might want to think of it as like ice and water to give you a real sense of it. And the dark matter is in these two different forms. Inside galaxies, it's one form. Outside of galaxies, it's the other. So we need creative ideas. Basically, that's what we need. And we're theorists are very, very clever. They're very creative. They have tons of ideas. And the trick is to come up with an idea that's testable. And because if it's not testable, it's not science, and that feeds in very well to the whole Bay Area skeptic idea. It's got to be testable, and so we'll just keep on thinking of new ideas. One final thing that is really neat. So I told you the Dama experiment had a certain sensitivity. We now are able to do things 100,000 times more precisely and more sensitively. But we are very closely coming to having dark matter detectors that are sensitive enough that they're going to start seeing the neutrinos that were made in this big nuclear explosion that we call the Big Bang. We're going to see cosmic relic neutrinos from the Big Bang. And if that happens, then that's going to be kind of hard because those neutrinos are there, even though we haven't found them yet. Once we start detecting them, if dark matter interacts less strongly than those, then we'll never see them because it'll be like looking for or trying to hear a whisper in a rock concert. So we're going to have to be very clever about that.
Well, that's really cool. Yeah, and I love your analogies, Don. I got another question for you from someone who might know a little bit more about this than me. So we have Jill Tarter here. I suspect you know that name. Do the different values for H, is that H naught, that come
Yes.
from two different measurement techniques have anything to do with dark matter?
Okay, so for those people who don't know what Jill is talking about, and it's a good question, Jill. So H naught is the expansion rate of the universe. So this is called the Hubble constant. So it's kind of neat. And Hubble discovered this in the late 20s, that if you look at a certain distance away, a galaxy a certain distance away from ours, the galaxy is moving away at a certain speed. And approximately moves away at 70 kilometers per second for every million parsecs of distance in rough numbers. Well, there are two different measurements of this expansion constant. One is just looking at nearby galaxies, and by nearby galaxies, I mean galaxies within tens or hundreds of millions of light years away from the Earth, so they're very, very close. The other one is looking at the radio signature of the Big Bang, what we call the cosmic microwave background radiation. And if you study that and you use your measurements of this thing, which occurred 400,000 years after the Big Bang, so the universe is 14 billion years old. This is only 400,000. So it's basically just, it's a baby picture of the universe. If you look at what you see there and you use the models that you have of how the universe was created and evolved and so forth, you get a different expansion rate. It predicts a different expansion rate of the universe that you see now compared to what you see by looking at nearby galaxies. And these things don't agree, and they don't agree by an amount that, if you look at the uncertainties of both measurements, they truly don't agree. So we don't know what the answer is. Could dark matter be part of this? Yes, absolutely. And the reason I say that is because when we look at this baby picture of the Big Bang and we try to project forward from that baby picture to what we have now, we need to have a certain amount of dark energy, a certain amount of dark matter, and all of those things come into play to make that prediction. And so, since we don't really know what dark matter is, obviously it has the potential of changing those predictions, and that could be the answer. I don't know that it is the answer, but it's clearly something that we'd want to get a better handle on before we know definitively. So yes, basically. Great question, by the way.
I hope we have if you'll give us a little bit more time, Don. I got to finish on this one, since this is the Bay Area Skeptics. I got to ask this one. This question is from Jordan Williams. Could all this be interaction from another dimension?
Well, Jordan, that's a great question. And that is very, very tricky, because when you ask about another dimension, it's an easy word to say, but scientifically, you have to be much more precise. So, for instance, one idea that people have often said is, it's kind of like the idea of ghosts, for the lack of a better word. Say there are ghost galaxies, and there's like our universe with a three-dimensional space, and then there's some ghost space somehow. And the gravity, in that space, there are galaxies or something like that. And the two dimensions somehow interact gravitationally. So that's one idea that's very, very common. And maybe that's what you're asking. And I'm not sure, because one has to be very precise. But let's say that's what you're asking. So if that's the case, I think we can rule that out definitively. And the reason I can rule that out is the following. Gravity falls off as 1 over the distance squared. So that's what you learn in freshman physics. So what you might not know is that 1 over r squared, that 2 in the squared, says something very, very important about the number of dimensions of space. So in a two-dimensional space, if you put you have some point source and you put a circle around it, the circumference of that circle in a two-dimensional space, the circumference goes as 2 pi r, so r to the 1 power. 2 dimensions, that r is to the 1. In a three-dimensional space, it goes through a sphere, 4 pi r squared. So a three-dimensional space, that's r to the 2. And then if you had a four-dimensional space, it would go r to the cube. So the number of dimensions that you have, whatever it is, call it n, that number on that r is the number of dimensions minus 1. And so if there are other dimensions, presumably those other dimensions have places that gravity can zoom into. And then that means gravity doesn't just go into our 3 dimensions of space, it goes into the dimensions of our space, plus the dimensions of this parallel universe space. But we then have measured gravity, and gravity falls off as 1 over r squared. So we know there are 3 dimensions. There aren't more. So that's one example of when people talk about other dimensions. Well, then if gravity could flow into those other dimensions, then we would expect it to have a dependence that's different than 1 over r squared. So that particular model, no. Now, if you have a different model, then maybe we could talk about how we would measure that. But that's a very common question that people ask, the sort of ghost dimensions. And we can say quite definitively that isn't the case.
Well, I want to thank you so much, Dr. Don Lincoln, for spending some time with us and giving us such an interesting talk and being so generous with your time and answering questions and things like that. I want to once again promote his books, especially this one, Alien Universe. Go out and buy it. Buy 2 or 3. Christmas is coming, so buy 2 or 3 and give them out as gifts. And check out Don's YouTube channel. Look at his videos; they're so cool. Check out if you do the great courses. You want to listen to something that's really, really extraordinary in your car. Check out his lectures on the great courses. And once again, thank you, Don. This has been a total pleasure.
Well, thank you, Bill. I enjoyed it.
All right. Well, I think we've come to the end of our presentation. We're going to have another one soon. Go to Bay Area Skeptics website, Bay Area Skeptics. It's baskeptics.org, and check out our schedule for the various things that we do. And I'll bid you all good night.
Good night.